All right, let's move into the meat of multilinear relationships. Mind you, chapter 17 does not involve any powers, any logarithmic functions, or other transformations of the basic input variables. Everything we're dealing with will have a linear relationship, and since there are more than one, we call them multilinear relationships. All right. You are all familiar with this equation from your junior high school math class. Y is equal to mx plus b. That is the equation of a line. It's called the point-slope equation of a line. In a Cartesian coordinate system, y is the y variable, x is the x variable, m is the slope, and b is the y-intercept. We can switch it around a little bit and call it y equals b plus mx, and there's no confusion there, right? It's the same equation. We can change how we name it a little bit. Instead of calling the m the slope, we're going to call the slope b sub 1. So b sub 0 is going to be the y-intercept, and b sub 1 is going to be the slope. So we're just giving them slightly different names, nicknames, if you will. And now that we're going to have more than one, we can make an equation that looks like this. The overall y is going to be the intercept plus the slope of the first variable times the value for the first variable plus the slope of the second variable times the value of the second variable, etc., till the slope of the last variable times the value of the last variable. And these are all different iterations of the same kind of idea. So a multilinear relationship between some output variable y, which is this over here, and multiple inputs, x sub 1, x sub 2, all the way up to x sub p, is a formula of the form, and then I put the same formula up there. So that's what it looks like. So we're just getting used to how we're going to write this equation. And the idea, the visual idea here is a slope. So b sub 0 is the intercept parameter, this first one right here. And then all these m's are known as the slopes. So these are parameters that are called slope parameters. They measure the effects of the input variables. So m sub 1 measures the effect of the x sub 1 variable. So they measure the effects of the input variables on the output y and are usually of primary interest. In other words, what we want to know is how much do the m's affect the y's. All right, so, for example, if you were trying to value a car, an oldie like this, and you say, what's that car worth? An old Jag like that. Well, how much does the value of the car go down if it's 1 year older, but it has the same mileage? So if you were looking at two of them, and one was simply 1 year older than the other, but they have the same mileage, how much would the price go down? Or would it? Maybe it goes up. How much does the value of a car go down if it has 1,000 more miles, but the same age? These are the questions that we're going to be looking at in this section of our study. So, to drive the point home, I'm showing you here the NTC salary data from chapter 17. This is 274 employees of a training company. And their employee ID numbers are in column A. Their ages are in column B. The number of years of experience they've had with the company is in column C. And in column D, we have the number of years of education that they have. And then in column E, what their salary is. All right. That's all fine and good. So we have 3 input variables and 1 output variable. Age, does age affect salary? Perhaps. Does experience affect salary? More than likely. Does education affect salary? You, as a college student, hope so. All right, so the first thing I do is I go in and I do a scatter plot of age versus salary. And I get this green graph here that says age versus salary. And then I ask Excel to put a trend line through the data. And it would appear that every time age goes up by 1 year, Y goes up, look at the slope, by 1.5034. And that's in thousands of dollars. So that would seem to indicate that each year of age adds $1,503 to the salary. Old guys like me like that. All right, we do the same thing with experience. All right, so I do a scatter plot of column C versus column E and did an XY scatter plot. And then I ask Excel to draw a trend line through it by right-clicking on any one of the dots. And I got this line. And the equation of that line is Y, or salary, is equal to 1.808 is the slope. So that would tell me that for every year increase of experience, that would add $1,800 to my salary. Okay, that's good for the people that like to hang around. Then you go over here to the third one, which is column D versus column E. And you go, wait a minute. The trend line through the data, through the scatter plot of education versus salary, has a negative slope. That would tell me for each additional year of education, I would earn less money. It goes down by $3,236. Huh? How could education reduce your salary? All right, we're going to put this aside for right now for just a little while and take a look at an equation that wasn't made one at a time. We're going to look at the equation that this chapter helps you develop, which is the multiple regression equation, a multilinear equation of this form. And it looks like this. This is the output. So this is just to kind of give you a preview of where we're headed here. And you can look at the coefficients that I've captured in the equation here at the bottom. The coefficients are over in the first column here. So you would be able to predict salary if you knew the age, experience, and education of a candidate. And you would say it would be equal to 13,672. And it looks like every year you get older, salary goes down. Oh dear. But experience goes up by $2,180 per year of experience. And it goes up by $2,874 for each additional year of education. Interesting. So this is where we would be able to predict how much a particular candidate should make. So this is where we are headed in this particular chapter. So this particular equation tells me that if two people, you got a Fred and a Jim, and they both have the same experience and education levels, then Fred will have an annual salary that's $85 less if he is a year older than Jim. In practical terms, then, age has almost no effect on salary. Nevertheless, if you plot salary against age, you'll see a very strong positive relationship. We did that before. And we saw $1,503 per year of age on average. So, if this equation is correct, this must be all due to older employees having more experience and getting paid more for the extra year of experience, not the extra year of age. So there's an overlap between some of these impacts. That's what we're trying to show here. Does experience drive salary? According to this, that says that an extra year of experience will add $2,180 to the annual salary, as long as age and education is held constant, which is significantly larger than the 1,808 that we predicted in the previous slide. How about education? The formula says that the effect of another year of education is to add $2,874 to your annual salary. This is almost the exact reverse of the data plot that we did in the previous slide, which showed that education had a negative impact. So, suppose the employees with more education happen to be younger. This is probably true in many workplaces. Specifically, suppose that the employees with one extra level of education are on average 2.8 years younger. So this would probably have 2.8 years less experience. So their salary is $2,873 more for the extra level of education, but it will also be $6,104 less because of the reduced experience. So in total, you tend to make a little bit less. So this does not mean that education is a bad idea. So this is pretty much what we saw in the data. Most people would agree that $2,873 figure measures the education effect, and that the negative number for experience on education gets mixed up with some of these other variables. So this is a great formula that we're going to be used to be able to predict salary of a specific person, or predict what would happen to salary under rather complicated scenarios.